Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to talk about the t-distribution, and this distribution was originally introduced by W.S. Gossett, and historically speaking, this guy published his work under the pen name Student because his company did not permit publication by employees. Therefore, the name of the t-distribution is also famously known as the student t-distribution, and because of its importance, the t-distribution has been tabulated extensively, similar to what you have seen in the standard normal distribution table. And the good news about it is, by having the results in a table, then we don't have to resort to integration process. So you don't need to integrate the probability density. Let's say the probability density is given by fx. You don't need to do this process here because the result of the integral here is already tabulated in the t-distribution table. And usually when the number of degrees of freedom is 30 or more, the probabilities related to the t-distribution are usually approximated with the use of normal distribution. Okay, so here is the important result, which relates the relationship between two independent random variables here. So here we've got y and z, they are independent, where y has a chi-square distribution with v degrees of freedom, and z here is a standard normal distribution. Therefore, when you combine y and z in this manner, so you have z over the square root of y here is the chi-square distribution, it is a random variable, and y is divided, you divide y with its degrees of freedom, and the result of it, for simplicity, you can call it t if you want. So t here is going to have this t distribution with v degrees of freedom. So this is our random variable, because z is random, y is random. The result here, t here, is going to be another random variable, and t here will have a t distribution with v degrees of freedom, where the probability density function is given by this one. It looks very much cumbersome if you want to integrate this function in order to find the probabilities associated with this random variable. Okay, and for that reason we have a t distribution table, and we will see example of this application later on towards the end of the video. Okay, now based on this important result, it gives the next important result, which is this one right here. So it says here that if x bar and s squared are the mean and variance of a random sample of size n from a normal population with mean mu and variance sigma squared, then the result that we have here, so this one here, will have a t distribution. Well, in this case, the name of this random variable or statistic is t. So t here will have a t distribution with n minus 1 degrees of freedom. Well, have you seen this before? Of course, you have seen this before in hypothesis testing. In hypothesis testing, there is a step where you have to calculate the t-statistic, and you use this formula here to obtain the value, and then you will compare the value with the critical values in order to decide whether you should reject or accept the null hypothesis. Right, now let me just explain a little bit about this result here, and I'm going to relate this result with what you have seen previously on this page. Okay, so next, what we have here is x bar and s squared are the mean and variance of a random sample of size n from a normal population. That means you can imagine we have the population, the random variable, the original random variable from a population, normal population with mean mu, variance is sigma squared, And then you imagine drawing a sample. So you draw a sample from this. So you draw a sample from this population. And from that sample, you are able to get x bar and s squared. So x bar and s squared come from that sample from a normal population with mean mu and variance sigma squared. And then based on that, if you apply this statistic, this is statistic, this is statistic. So if you apply that into a formula as such, x bar minus mu s over square root n, the result here, for simplicity, you can just give another name. For example, you name it as t. T here is going to have a t distribution with n minus 1 degrees of freedom. That's what the results tell you. Okay, so I'm just going to show you how this becomes a t distribution. So why is this a t distribution? Now, why is this a t distribution has something to do with the result, the important result that is given here, where it says when you have a standard normal distribution, and this one here is a chi-squared distribution, in this situation, in this formula, then the result here is going to be a t distribution with v degrees of freedom. So what we have here is this guy, and I'm going to show you which part of it relates to a standard normal random variable, which part of it relates to the chi-square random variable, and that's what we're going to do next. Okay, so here we have this statistic. So we have t is x bar minus mu s over square root n. Well, what I can do is I can introduce or rewrite this part in terms of, okay, x bar minus mu times with 1 over s. This is s over square root n. Okay, now in order to make sure that it looks like this, it looks like z. What is z? Z is the standard normal distribution. I can see that this part here can be easily turned into a standard normal random variable if I have x bar minus mu over sigma, and here is over square root n. Why? Because originally we have this result here, x is normal with mu and sigma squared. Therefore, I know x bar, based on the idea of sampling distribution of the sample mean, x bar also is going to be normal with mean mu sigma squared over n. And therefore, based on this, if I'm able to divide this with sigma over square root n, the whole thing here is going to be z. It is going to be a standard normal random variable. And I have shown this in the previous video related to chi-square distribution, and I've talked about it in the sampling distribution of the sample mean. Right, so if I want to divide that with sigma over square root n, if I want to introduce sigma over square root n here at the bottom, sigma over square root n has to be introduced at this part as well, because we cannot just simply introduce something and change the whole expression here. We need to maintain the original expression. Okay, all right, let me just reiterate this process again. Maybe it will be clear is if I write it in terms of like this. Okay, so now I'm going to introduce, okay, x bar minus mu. I'm going to divide that with this guy, sigma over square root n. This is what I'm going to do. And because of that, the bottom part also have to be divided with the same thing in order not to change the original expression, right? Because by doing that, it is as if I introduce nothing, because this thing here, when they cancel out, it becomes just 1, and you get back the original expression, which is this one. Okay, so by doing that, I have already turned this part here into a standard normal random variable, so I can just call it z for simplicity. Okay, so this part here becomes z already. So now it is looking a bit like this first theorem that we have. We have z at the top part here, which is a standard normal random variable. So this one here has a standard normal distribution. Next, what is going to happen at the bottom part? So you can see here the bottom part, well, I can write it in terms of like this. I hope you can see that sigma n and sigma n can be cancelled out. So here we've got, you can cancel out this guy and this guy. So the bottom part is just s over sigma. Okay. Next, what I can do is I can express it in terms of a square root, because, okay, again we go back to the original result. We recognize there is a square root of something, the square root of y over v. What is y? Y is the chi-square random variable. Okay, so if I want to apply the square root, what I need to do is I have to express it in terms of s squared over sigma squared, right? Okay, so if you consider this part, if you want to take out the square root, you will get back s over sigma. So now we've got some square root inside. Now what I can do is I can introduce another term, because this is what you have already learned in the chi-square distribution. When you have n minus 1, s squared over sigma squared, this one here is a chi-square random variable. So here is a chi-square random variable, and therefore it will have a chi-square distribution. So here what we have is we are going to introduce right next to s squared here, we're going to introduce n minus 1 over sigma squared. Okay, so therefore we have z. So here is s squared. I'm going to introduce n minus 1 over sigma squared for that part. And of course, if I don't want to disrupt the stability of our terms, our expression, what I need to do at the bottom is I need to do similar things at the bottom. So sigma squared here, and I have to introduce the same thing, which is n minus 1, oh god, I'm so sorry, over sigma squared. Okay, right, let me try and see if I can write it with better clarity. So here is the whole thing, the square root of the whole thing. Okay, so by doing this, like I said in the previous explanation, well, I have said that before, this is the same thing as introducing nothing, because you can cancel out this term from top and bottom and you get equal to 1. So when it is 1, then you go back to this original expression. So you're not changing anything, even though you introduce something into this expression right here. Okay, so next what we have to do is, you can recognize now, it looks like z, the square root of. Now I can call this another random variable. I can call it y. And like I said, this one here, if I call it y here has a chi-square random variable. How do I know this? Well, I have explained about this in the previous video related to the chi-square distribution. So if you're not sure what's going on here, I suggest that you refer to the previous video related to the chi-square distribution. Now, based on this, I can recognize that this is a chi-square random variable, which I can just simply call it y. So the whole thing here can be represented as y divided with, so I hope you can see that this term here can be cancelled out with this one. So here we have n minus 1. So can you see how this presentation of our result here looks similar to the important result given by the first theorem here? So we've got something which is a standard normal random variable at the top. So here is z, and we have the chi-square under this square root divided with v divided with something. So v here, or this something that you divide y with, is the degrees of freedom. So this one here is the degrees of freedom, and you can see that degrees of freedom is equal to n minus 1. Therefore, I can say that this now looks like this: y over v, I can call it v, where v is equal to n minus 1, and v here is representing the degrees of freedom. And this is the result given by this one here. So this one here comes from the idea of this one, and you should be able to know that this is the direct result that you can apply in the hypothesis testing, in the case where the samples that you get come from a normal population with mean mu and variance sigma squared, okay? But maybe the sample size is small and you just get the sample variance or sample standard deviation to work with. Okay, right. Let's move on to example. So here we've got 16 runs. That means we've got 16 samples. The samples is the result of the 1 hour test. And here it says the gasoline consumption of an engine averaged 16.4 gallons with a standard deviation of 2.1 gallons. And this statement here related to the result from the sample. Therefore, this value here is x bar, and this one is s. Okay, standard deviation, just s. So test the claim that the average gasoline consumption of this engine is 15 gallons per hour. So talk about average gasoline consumption. You're going to test the claim. So this is about mu, okay, the population mean, and mu is equal to 15. And use alpha 5%. Well, in the first step, we're going to start off with formulating the hypothesis statements, which is mu is equal to 15. So this is H null, and H1 mu is not equal to 15. So the statements have to be contradictory. Next, step 2 is where you calculate the test statistic. And since the sample is small and we only have standard deviation to work with, therefore we can use the formula, which is this one, x bar minus mu s over square root n. And this is the formula which you have seen given here. And this random variable actually has a t distribution with n minus 1 degrees of freedom, and that's why for hypothesis testing for this particular problem, you will have to refer to the t distribution table, okay? And the result here is going to be 16.4 minus 15, and then standard deviation is 2.1 divided with 16. So you should be able to get that the t-statistic is 2.67. Next, on the third step is we're going to obtain the critical values. So this is how the t-distribution looks like. It looks symmetric, and we have alpha 5%. Since this is a two-sided test, therefore we have the critical regions on two sides of the distribution, where this area here is going to be 0.025, this area is also going to be 0.025. Total up will be 5%. In order to decide whether we should reject or do not reject the null hypothesis, you need to find the critical value, which is at this point and at this point. So you can refer to the t-distribution table, which is this one. This distribution table gives you the area from one point to the right, and here what we are looking to find is this area, where this is 0.025, and this area is also 0.025, but because they are symmetric, we can just focus on this part on the right hand side of the distribution. So area here is 0.025. Go to alpha. Alpha here represents the area, 0.025. Now the degrees of freedom for this is n minus 1, which is 16 minus 1, which is 15. And therefore the critical value is 2.131. So that's the critical value, 2.131. And because they are symmetric, another critical value is negative 2.131. So critical value is plus minus 2.131. And the fourth step is you're going to compare the result that you have here with the critical values that you obtain in step 3. So you can see that 2.67 will be somewhere here. So this will be the position of 2.67, which falls into the critical region. Therefore, you are going to reject H null, since the test statistic 2.67 falls into the critical region. Okay. Next, what you can do is you can come up with a conclusion. So the conclusion is enough evidence to say that the average gasoline consumption is not 15 gallons per hour. Okay, so this is an example of direct application for this result given here. Okay, so just to reiterate, let us start from the beginning. So this is the idea of t-distribution, where if the original theorem says here that if you have two types of random variables, y and z, y has a chi-square distribution and z has a standard normal distribution, then the combination of those two in this setting here will give a new random variable, and this new random variable will have a t-distribution. And this result here is translated into what you are seeing right now, which is this one. And this formula here is quite familiar because we have seen this in hypothesis testing before. And why is this thing has a t-distribution? Well, I have shown you how that can happen as such on this page right here. And the application of this formula here can be seen in this example. Okay, I think that's all for now. Thank you very much for watching.